Welcome everyone to the OpenPlanetary Virtual Talk. Today we have Mr. Amitabh sir from Space Application Center ISRO at Ahmedabad, India. Thank you, Amitabh sir, for agreeing for this talk by taking out precious time from your schedule. Mr. Amitabh is working in ISRO since 2 decades after completing his MSc in Electronics and MTech degree in Remote Sensing. He has expertise in image processing, satellite photogrammetry, planetary data processing, and cartography. He is currently the head of Planetary and Space Science Data Processing Division at SAC ISRO. He is serving as the Deputy Project Director and Operation Directors of Chandrayaan 2 and 3 missions for the optical payload data processing. So, over to you, Amitabh, sir.
Yeah, thank you, Fazpal Singhji, and thank you, organizers, for giving me the chance to give a talk on the topic uh, Chandrayaan mission data processing from raw signal to insightful data products. Are you getting the slide?
Yes, sir. Yes.
So I'm going to talk about uh, what type of data processing we are doing to make the input signals, whatever we are receiving for different payloads, uh, uh, that can be used by the users. So particularly for the Chandrayaan mission. So if you see, the objective of data processing is to provide the data products from our science payloads of different interplanetary missions to the scientific community in a format which can be used by most of them, and it should be with reference to the global data standards. So globally, this is planetary missions are long life missions where today we generate the data. We don't know the use at that time. It is limited by our knowledge. So if we progress with the time, the same data having more value than the previous one. So that's why it should be a global standard. It should be comparable with other data sets. With that, it should work. So most of the science payloads, whatever we normally take for planetary exploration, is based in the different electromagnetic spectrum regions, like optical region, microwave, X-rays, or UV regions. So till now, ISRO has sent 6 missions out of the Earth's orbit, and out of these six, 3 are moon missions. As you know, 2008 we have started with Chandrayaan 1, the first mission to the moon, our first planetary mission, and then followed by Chandrayaan 2 in 2019, and third mission of Chandrayaan 3 in 2023, where we have landed on the moon. So the main application of the data product, when we are processing the data and generating the product, we should keep in mind that we are going to use that for the how the planets have got formed, like moon case, how the moon formation was, what is its age of different regions of the moon, how it has evolved during the years, and then its surface, what is on the surface, what is the properties, what type of geomorphology is available there, different features, characteristics, then interior properties also we want to know. Then another thing is water and water ice. That is the main crux, that if a human has to go there or if life exists there, then we have to find some water and water ice related components are there or not. Then finding the places where human settlement or human base can be placed there on different planets, particularly on the moon. Then future space tourism already has started, but moon also one day this type of tourism we can foresee. Then mining of moon, and another thing is platform to reach the far planets, which is far from the Earth. So this can be used as a platform for going there. So these all things we should keep in mind, and then we are processing the data. So this is the basic our reception, data reception and data product generation system workflow, where normally this is a typical case for Chandrayaan 2, and each payloads on each of the orbiter, whatever orbiter carried certain number of payloads. So each payload having a principal investigator, having the instrument scientists, and that depends on the sensor operation, what type of operation it is, or what should be the timing, and those things. On that basis, one planning cell is there, mission operations planning is there. So it plan for a particular payload operation depending on, suppose a orbiter contains 6-7 payloads. So each is having, some is day and night imaging capability, some is having only night imaging capability, some is day, some is in X-ray. So giving a particular time slot for a particular payload to complete the observation, whatever asked by the principal investigator. So that type of mission planning is there. Then it's sent to data acquisition and telecommand system. There we give the command and finally acquire the data through payload acquisition system. So from the payload acquisition system, we have two flows. One is going to processing. Means whenever it is acquiring, if it is, suppose in case of moon, it is near side of the moon, the acquisition is directly, data is getting dumped on the ground station. So same time you can get its view that it is giving the correct location or not, or having some problem, or data is correct. So those things quick look wise we can see there in the near and real time mode. While another goes to level 0 data processing, where all the transmission errors, other things have been removed, and then level 0 voltage or whatever current that form, it is getting stored. And then I will come to the definition. Then we have the data processing and archival system. This system generates different type of data products, and this is depending on the payload. It may be at the payload operation center in individual units of the ISRO, or it is at ISSDC also. And finally, data is getting processed different payload operation center and ISSDC. And finally, archive all data at ISSDC in the PDS-4 data archive. PDS is a planetary data system. Currently, fourth version is going on. So there we have the data archival system where we are stored. Then we have browse and dissemination system where these data, thumbnails, other things, all details, level files are there that user can browse from their terminal through internet, and then they can see the data at that particular place or the different regions, it is there or not. They can order that and then download also. So these data sets are freely downloadable, most of the data sets, and that way our whole data product generation system works. Then coming to planetary data system, as all who is working in this field in planetary science, they know that it is a well-known established archival standard proposed by NASA long time back for all the planetary missions. So most of the data sets archives and distribute in this standards for all the planetary missions, and it ensures the long-term access and usability of data, because we don't know tomorrow after a few years who is going to use. So this data is self-structured, peer-reviewed, well-documented, and freely available. Whatever has been done with the raw file, whatever we receive directly on the ground station, then what type of correction, other things has happened, everything is well documented, so that tomorrow somebody goes through those documents, they will be able to find that what has happened to this data, and is there any chance to upgrade that, those processing or algorithm wise some changes are required, so those can be done in the future. So, and this data system was adopted by several, nearly all the space agencies, and till now, 4 versions have been released. As you know, Chandrayaan 3 was launched in 2008, so our Chandrayaan 3 data, most of the payload data in PDS-3 format that time. So after 2012, PDS-4 was adopted, and it is improved version. It is having query, other things are simpler. So that way, PDS-4 came in 2012, and now PDS-4 is stable, and most of the missions and coming missions, future missions, we are going to use this PDS-4. Even for Chandrayaan 1, for 2 TMC and hyperspectral camera, those payloads data already we have converted into PDS-4 and hosted for the public use. So on the same line of the PDS, ISRO has developed their own ISRO Science Data Archive, established in 2008 at Indian Space Science Data Center, Bangalore. And it is a central repository for all scientific and engineering data by different ISRO's planetary missions. Yeah, so coming to Chandrayaan 1 mission, we have some 11 payloads there. Out of that, 5 payloads is from India and 6 are from different parts of the globe. And these all data sets have been provided in PDS3, and the main aim was to do the topographical, mineralogical, chemical mapping of the moon surface. So the payloads are in the X-ray, visible, infrared, and microwave regions. And I will give you examples of the optical region, how we have acquired the images, what are the images available for the public. And each and every data sets are available for the Indian payloads at the Indian node, while on the US node also, this PDS node, this all 11 payload data sets are available. So any either our ISRO side or NASA side, these all data sets are you can access seamlessly. So these are the coverages of terrain mapping camera, one of the camera which is having the 3 sensors, and those 3 sensors actually having 4 aft and nadir, 3 camera. It takes the 3 images, then it generates the stereoscopic views, and finally stereoscopic processing using the triplets and generate the elevation model height at different places. So you can see the globe wise whatever coverages was there that has been shown here, and black regions was not covered since this mission was lasted for 312 days. So these are the levels of the data product. Once that we receive the data, suppose for the TMC, then the basic definition wise, level 0 is instrument size data, which contains raw voltage counts at full resolution, then time order and transmission errors or duplicates. Suppose in transmission, sometimes the previous packet comes before the main packet. So those errors are getting corrected or removed. So that is the level 0. Then level 1 is radiometrically corrected. Suppose it is a camera, then photo response non-uniformity will be there between the CCDs detectors. So those is getting corrected. Then some losses are there due to the misbehavior of the different detectors. Some of the detectors doesn't work for full time of length of acquisition, while few of them sometimes it works, sometimes it don't. So on that basis, these losses are there in the line direction or pixel, means rows direction and column direction. So that is getting corrected. And then also the position where it has started the acquisition, that is also getting attached with that. So here the position is also there in level 1. Then level 2, it is the fully corrected data with the all the whatever image suppose it comes, it is correlated with the ground, and given the image to ground transformation where each pixel, each element of the image is connected with one latitude longitude value. So that is one. Another thing is it is corrected with respect to terrain or topographic and make it the ortho image, or it is a map like product. Then several geophysical parameters also. So this is called now derived. So now in PDS4 there are 3 processing levels only are there, that is raw, calibrated and derived. And all the data sets we are putting in this. So if you see the a typical processing pipeline for an imaging sensor like TMC, we have ancillary data coming from the mission, that what time it has been proposed to acquire and what will be the orbit, other things. Then level 0 payload raw data, and from there we start with these 2 inputs, then do the radiometric correction, then find the do the cellular tagging. How it is getting done? One is through the star sensors, because we know GPS is not there on board for the moon missions, it cannot work. So we have there the star sensors inertial system. So that gives us the one attitude and orbit value. On that basis, we compute one latitude longitude there. But another thing is it is off by whatever the accuracy level of our star sensors. So that needs to be corrected. So corrected through the auto LCP, auto lunar control points. So it is getting generated with the references base maps, whatever earlier at the Corsa resolution available. Like Selene ortho image is available from the JAXA, and Clementine and WAC, LRO WAC ortho images are from the NASA. So these are the references we are using to just update those coordinates, latitude, longitude, that is coming some offset there. So then do that process, whole process is called resection. Then after resection, we provide that actual corner coordinates and then put the level 1 PDS4 data archival. We send it. Another thing is for the derived product for like TMC, terrain mapping camera, we have to derive the digital elevation model and ortho image. So there we do the image matching between all the three images, find the same feature in different images, large point clouds we generate, do the intersection, means calculate the parallax between the images. That ultimately gives us the elevation at those points, and then we do the regularization of those elevations, and finally generate the digital elevation model at every 10-meter interval. And then from the same DM you use for the ortho correction of the image, and finally level 2 product we archive. So this is the full typical chain of imaging sensors. So these are the few examples where raw data you can see here, photo response non-uniformity between the images. Lines you are able to see different places that has got removed in the calibrated data. Similarly, here in the hyperspectral of the camera, you can see these black lines. This is bandings. So these bandings are coming when the certain detectors are not working uh, around the full acquisition period. So that's why this line is coming. These are the line scanners. So it scans in the push broom mode the line. So if the one detector is not working, it is putting black band throughout the acquisition. So that is also having some algorithms through that it has been corrected, and now you can see a calibrated image that is not there. So this is the digital elevation model approach. As I told you in earlier this one, we are having the 4 nadir and aft camera. 4 camera is looking at 25-degree forward, aft camera is 25-degree backward, and nadir camera is looking just below from the spacecraft. So this is giving the nearly 20 kilometer of swath, and with all three images are nearly only 56 pixel out of the 4K pixels, 4000 detectors are there in a line, and this is a line scanner. So out of that, all three can only shift off the 56 pixels in the across track direction. While along track direction, there is a time gap of 60.3 3 seconds. Means 4 to aft, all same place we want to capture, it can capture in nearly a minute time. So that temporal deviation is also not much. That's why the illumination conditions on the moon surface is very important, because feature changes its look and feel when the illumination angle of the sun changes. So here only 1 minute difference. So illumination wise very less difference. So matching of these images are very promising, and that's why it is getting used for the digital elevation model generation. So what is the basic principle? We have the triplet, these three images, then generate the two images we take at a time, generate one match, then correspond to the third image, again repeat for all three. So like that we get the reliable points on the moon surface, point cloud on the moon surface, and those point cloud we calculate the space intersection, which says compute of the parallax between the same, and then correlate with the whatever lunar control points are there. With that, few lunar control points are needed, that we automatically generated in an image. Suppose one orbit of some 1200 kilometer, we require some 20 to 40 type or 20 to 30 type of lunar control points to model that. Then using that we calculate the space resection, and finally we have the digital elevation model and ortho image of that place. And this is the formula. You can see the smaller triangle with respect to this bigger triangle. DH, the height elevation can be computed by the formula given. So this is the simple formula, but intersection is a process where you have to put a circle. It is not directly, it is going to give you this height. So parallax, what type of parallax is acceptable, what limit you will accept, those things have to be put model here. Then these are the few products available from the Chandrayaan 1. This is the digital elevation model, ortho image. The height is color coded. You can see the contours and the 3D visualization of that in anaglyph mode. The through filters you can see here basic, very small scale features also you will be able to see. Then visualization like 2.5D means, and then walkthrough also you can do above certain heights and see the how the feature will look like if I change the illumination or change the height exaggeration. Then we have these two polar mosaics where you can see the black regions that has not got covered, and that is why Chandrayaan 2 we put the same camera again, and then we are trying to cover those regions. Then another one was hyperspectral, where this is having a spectral region 0.4 micrometer to 0.95 micrometer region. It is having 64 bands with 16 nanometer spectral sampling with a spatial resolution of 80 meters. So here the detection of mineral and other things are easier. And one of the example is titanium distribution for a particular orbit acquisition has been done, and it is shown here that what is the concentration of titanium on the moon surface. Similarly for silver, gold, those things has been done for this. So these data sets are available on our Pradan site. Then coming to Chandrayaan 2 orbiter payloads, this was the supplement to Chandrayaan 1, at least orbiter payloads. Whatever was not done by Chandrayaan 1 payloads to fulfill those goals like terrain mapping camera and IIRS, imaging infrared spectrometer, and few more are there like dual frequency synthetic aperture radar. That was the first time dual frequency L and S band radar was placed on the moon surface, and for the full polarimetry, getting the full polarimetry for the polar region. We have IIRS. IIRS is a large spectral region, it is getting covered. Then we have CHASE-2, which is neutral mass spectrometer, which will carry out a detailed study of the moon exosphere. And then we have one camera called Orbiter High Resolution Camera, currently the best camera for the moon surface. And it is a region of interest based images it provides us, and it is quite helpful in the landing site selection. And Chandrayaan 3, in fact, whatever landing has happened, all images, all data sets, the reference data sets have been prepared by OHRC. So these are the statistics of whatever data products currently available. We have OHRC. OHRC having the capability that you can steer it at different tilt and then take the same view, same area view, and then generate the DEM. So a stereoscopic angle 30 to 35 degree. So for that you have to plan, and then it is a mono camera, not a stereo camera, but mono camera only. Two different orbits. You by giving the tilt, we can take acquire the stereoscopic multi-view images, and finally generate the elevation model at nearly 25 to 50 centimeter type of thing. But this product is only for the special user and for mostly for the landing site selection by different specimens. Then TMC2, as I told, this is the triplet stereo, and currently having the best DM resolution, surface DM resolution, like low light and 30 meter, but it is a laser altimeter. Here you have the texture will be finer in case of TMC, and it is having 10 meter type of DM is available. On request basis, we can go up to 5 meter type of DM also. Then IIRS, we have hyperspectral imager, best spectral resolution till now up to range wise, and it is having 256 band, and all here products are available. Then SAR also, as I told, dual frequency SAR, first time for the moon surface, and resolution ranges from 2 meter to 75 meter, and swath is nearly 10 kilometer, and whatever it is a unique observation for the full polarimetry type of thing. All the data sets are available in the Pradan website. I will come to that, show few of the screenshots that where to go for the data. Then these are the few data products from imaging payloads. You can see TMC2 coverage map. Most of the nearly 80% of the moon now got covered by the TMC and 90% for the IIRS. So polar wise, if you see, nearly 90% area has got covered, North Pole and South Pole. This is one of the example of our three images from three different cameras generated elevation, and you can see the depth here. Then TMC2 polar DEM, all the whatever left side it is showing the images, same digital elevation model is available for those regions. This is the one of the example of the how the looks like if you take the ortho image and DEM and just overlay on that and see. And these all can be done by any software like QGIS or any open software or IDL, NV, MATLAB. Anything can be used for the further results. Then these are the OHRC images. You can see here the eagle descent stage, the bottom left photograph, where the actual photograph taken by the astronaut, and the impression on the OHRC image. So you can easily find it out. Similarly, here in Apollo 12, you can see the flag pole shadow is also visible. Whatever flag is currently there, that pole shadow is also getting captured by this image. OHRC, and astronaut tracks and other things are quite visible. Each and every boulders also you can get boulders up to 1 meter. There is no problem. Up to 25 centimeter, we have to do the studio imaging. So that is the only thing. Otherwise, 1 meter type of boulder we can simply identify with the help of 2D images. And these are the one of the example that our Vikram lander, how it is imaged by different cameras like Dhanuri of the Korea, then LRO of the NASA, and then you can see the Chandrayaan 2 orbiter high resolution camera. So here clearly visible how much details are there. This IIRS imaging infrared spectrometer, it is having 256 band, I told, 0.8 to 5 micrometer range it is working with a 16 nanometer type of a spectral resolution and 80 meter spatial resolution with 20 kilometer swath. Here also, this is nearly 95% of the area from IIRS for the moon surface already got covered. And you can see here in different band how it looks like different frequency range and what is the spectral characteristics at different features there. So that is shown in the graph. And this is calibrated data sets, and few of the different exposure and gain settings are there. So few of the exposure and gain setting which was not done in lab currently is undergoing through the calibration using the whatever the data-based calibration is going on. These are the Chandrayaan 3 payloads, where we have the optical instrument like lander imager, rover imager, and navcam. So these has provided lot of data sets of the moon surface. As you know, lander imager was on lander. When it was landing, it was giving the images of the moon surface. Then rover imager was the image on the backside of the rover. Well, it has given the millimeter type of resolution of the moon surface, and navcam is a navigational camera images, left and right images. On that basis, the rover has moved on the moon surface. So those data sets are also released now in the public domain on 23rd August 2024 this year, and this is available in the public domain. Similarly, for lander payloads, three of the lander payloads. One is Rambha, that measures the local gas and plasma environment changes over time near to the lander. So that is also there in the public domain. Then Chaste, that is the study of the surface thermal properties. So that is also there, the temperature measurement there. Then seismic activity was recorded by ILSA, and those data sets are also provided on the site. So these all things are available in the public domain. Then coming to rover payloads, two payloads was there. That is alpha particle X-ray spectrometer, and that determines the elemental composition of the surface, like magnesium, sodium, aluminum, etc. So those data sets are also there. These all, whatever non-imaging payloads are there, those data sets are text files. Comma separated text files are there. Directly anybody can use, and with the level file. So anybody can see with the level that what time, what interval this data is there, and all things are documented well. There are some data product science interface specification documents are on the site. Plus the user guide is also provided for using those data sets. Then this laser-induced breakdown spectroscope, that is the qualitative and quantitative elemental analysis, and to derive the chemical composition and infer mineralogical composition to further our understanding of moon lunar surface. So this data is also available there. So APXS and LIPS data. So these all 8 instrument data sets are available for the Chandrayaan 3 now. So these are the details that what type of products are available. For imaging payloads, calibrated data sets are available for the images, while LIPS and APXS, calibrated and raw both are available, and other things, raw images are raw data sets are available, and all the image data sets are in NavCam, it is in PNG, while lander imager and rover imager, it is in JPEG. This is one of the example how the left camera and right camera images of the NavCam data is lying on the website, plus the level. What level tells what is the mobility ID, at what time it has been taken, with what was the sensor configuration that time. Those all informations are there. Plus one spice is also there, that is lying with the Chandrayaan 3 data sets. So if those informations, some of the information suppose related to geometry is not available here, that is with respect to mission, that is available with the spice. Similarly, for lander and rover imager data, also you can find this sort of data sets. With the image data, we have the level file, plus the calibration files are also available in the calibration folder. So now coming to these data sets, how we are disseminating these data sets. So this is getting disseminated through a browse and dissemination service that is lying at Indian Space Science Data Center, Bangalore, where we have two approaches. Earlier we had one Pradan, that is the policy-based data retrieval, analytics, then dissemination and notification system. So through that 2020, we have started for Chandrayaan 2 this type of. So it is having a generic web application to search, browse, and download through this URL. Then this is based on the specific parameters of the payload, that location, observation time, lat long, etc. But there was no visual appearance. So it has been felt that people were asking, the users were asking to provide the map-based application. So we have developed that map browse application, and now that is also available in the public system. So if you go there, ISRO Science Data Archive, in the Pradan, you will find this Chandrayaan 3, Chandrayaan 2 data is available. Chandrayaan 1 data is available directly on ISSDC website. And for the two payloads, it is available on the same Chandrayaan 2 map browse application website, which has been released this year in April, where we can access the data through the map-based and form-based search. Here, we have guided tooltips when you go logging through this application. A simple process is there to create the username. Once username will be created, after logging, you will get one tooltips that how to use this application, map browser application. So this is the Web Explorer, Data Explorer, web-based Data Explorer, where you can directly go see the data instrument footprint, then metadata file of the PDF product, then browse the image. Also, you can visualize what type of image is there, how it is looking like. So here the map browse is there on the Pradan side. If you click there, this type of this window will appear, and here you can see IIRS, TMC, then OHRC and SAR. These four payloads are there. So these all data sets for the Chandrayaan 2 is there. Then Chandrayaan 1, TMC 1 and IC. We have the tooltips. Through that you can get the change the projection, see the polar area. So here equatorial system area has been provided in the equirectangular projection system, and where the footprints are for the equatorial region. And for the polar region, we have polar stratigraphic projection. So you can see here the red colored thing has been same thing. Browse image also is there, that can be seen the what image is coming. Similarly, for SAR data, we have the polar area. It has covered the polar area mostly. So this is the polar projection system between 80 to 90 degree, and these are the sharp footprints. And if you click the one of the, you will get the image of that, and you can zoom that and see, and you can download directly from here, the download button. Chandrayaan 3 also data archival and download system has been developed through Pradan, and here all Ramba, Chaste, ILSA, leads, APXS, then cameras, LI, RI, NavCam, and SPICE. Those all informations, all data. If you click, you can go there, download date wise, or image you have to download, image you can download. So all 14 days images or 14 days data sets for these all Chandrayaan 3 payloads, and that is now available for the public. That is fine. With that, I will conclude my talk and tell that data sets are available. If users will use and provide the feedback, we will try to, if something is not there, we will try to put it there. Currently, it is all our PDS for compliant data sets, and as per the standard followed by most of the space agencies. Thank you.